Okay. Can you see my screen with assignment one?
Yes, sir.
Okay.
Yes, sir.
Let me see. I'm unable to write on this one. Just a, okay. Now you can see whatever I am writing, right?
Yes, sir.
Okay. Okay. Let's get started with the assignment one. If you have any doubts other than these assignments, you can ask me. Just let's finish the assignment first once. Okay. Okay. In the assignment one, there were some, I think, 10, 11 questions. So we will see these questions. You won't be able to see my face because the camera is working for this video recording. So I can share the video. Okay. So let's get started with this one. So okay, question number one says that the IC integrated circuit revolution was triggered by the invention of. There are certain things like these cathode ray tubes, transistors, diodes, and let us see one by one. What are the cathode ray tubes? Are the if you have seen, you have some big TV at your homes. So there, these are the cathode. These are the function of these TVs based on the cathode ray tubes. Okay. So in these, there is a fluorescent screen, and uh, uh, from the behind there is an electron gun, and whenever that electron gun hits, electrons hit the screen, so they close. So based on that, these are the like TVs works. Our home TV, which are big TVs were there. So based on that, they work. So and transistors are the switching devices, or these can be used for transistor are switching devices, or these can be used uh, for the amplification purpose. Okay, the tiny transistor, whatever you can imagine in your daily life, like from mobile phones, laptops, or anything charger, everything is based on these transistors only, because these switching is so fast, very fast, and based on these, all the electronic gadgets work. Okay. And another thing is the diode is a device, electronic device, which is like capable of carrying a current in the one direction. Okay, the current flows through the diode is one direction, and in the another direction, it blocks the current. It's not a, like a wire. In a wire, however we connect the battery, it will there will be a flow of current. But if we fix a diode in between the wire, okay, so what will happen? It will the current will flow in a one direction only. When you change the polarity of your battery, so in the another, in one of the polarity, it will block the current. Okay. Micro electromechanical systems, like these are the devices like a gyroscope or kind of these things. uh, these are like very small micro electromechanical systems. Okay, but the transistors are like the building block of everything. Okay, transistors are everywhere. Whatever you can imagine, your gadgets, anything you can imagine. are based on the transistors. Okay, so the revolution was triggered by the invention of the transistor in 1950s. Okay, 1947 or 1954, I guess. Okay, so the correct answer is transistors. Okay, so let me see. The next question is the spreading of the discrete energy levels. So, of discrete energy states into the continuum states. The discrete energy states are the states for the a isolated atom. So, let us say this is an isolated atom, whatever atom it is. So, there are states. These are the energy states in which electrons are always moving. Okay, so in a paper, if you are writing in a like energy band diagram or energy diagram, if you are representing it, you are representing it these by lines. Okay, these are the energy states. These are the like in a single state, only two electrons can be occupied. Okay, with the opposite spin. Okay, one is up, one is down, like this you have seen. So in these only two electrons can be occupied, and uh, upon reducing the interatomic distance, so when there are okay, this is an isolated atom, this is another isolated atom, but there is no connection in between these two. But when we bring these two together near to each other, so these electrons will feel an effect of the electrons from this one and the nucleus or protons from this one, these electrons. So the wave function of these electrons will overlap. Okay, wave functions of these will overlap. So because of the overlap of this wave function, so uh, these energy levels will split. Okay, these energy levels will split because at this energy level, two electrons can be occupied, and at this energy level, two electrons can be occupied. But when these will interact, or there will be a system of these two atoms, so there will be this energy level has to split because no two electrons can have the same set of quantum numbers. Okay, and that is because of the Pauli's exclusion principle. Okay, because this will make a system. This will make a system that will have initially it has the discrete energy levels, and another atom has the discrete energy levels, and which are at the same. These energy levels are at the same when these atoms are very far, but when they come close together, close to each other, so these electrons will feel a force by the another atom or electrons from the another atom. So there will be a splitting, and that is because of the Pauli's exclusion principle. No two electrons can have the same set of quantum numbers. Okay. Wait. Whenever you need any more clarification, you can ask me. Okay. So, and indirect band gap, this is a well-known silicon is an indirect band gap semiconductor which is 1.1 electron volt, and indirect band gap is the material with the conduction band minima and valency band maxima are at different values of k. This is k reciprocal space, k vector which is for momentum. Okay, crystal momentum, and this is the energy. Okay, these lie at different values of k. So this is the indirect band gap semiconductor. Okay, and a key property of the semiconductor that distinguishes it from the metals and insulator is okay. So there are certain things in semiconductors. In semiconductor, when you just at 0 Kelvin or whatever, there are uh, no electrons in the. This is conduction band. Let's say this is conduction band. This is the valency band, and this is the Fermi level EF. Okay, this is the EF of any item, of any material. Okay, and this is the semiconductor. Okay, so at 0 Kelvin there are no electrons in the conduction band, and if we increase the temperature T, you are increasing the electrons get some sufficient energy to jump to the conduction band. So there will be some electrons in the conduction band at let us say at the room temperature RT. At room temperature there will be certain number of electrons at the in conduction band, and these number of electrons can be tuned with temperature, with light, because with the light you are giving what you are giving the energy to these electrons here in the valency band, and they will jump to the conduction band. With light you can give, and with by applying a kind of electric field, you can give some energy to move the electrons from to change the concentration. Okay, and also the most the thing that is being done with the semiconductor is change in the concentration with doping. Okay, if you can dope the semiconductor, you can change the concentration of electrons or holes. Electrons in the conduction band and holes. Whenever we are talking about the electrons and holes, we always talk electrons are in the conduction band and holes in the valency band. Okay, so we can change the concentration of electrons and holes by means of doping, and you know, if the concentration of charge carriers increase or decrease or decrease, so then what happens is that then there is a change in the conductivity. Okay, there is a change in, so how what we can do is the ability to tune the conductivity of the material. This is the right answer. We can tune the conductivity of the material by means of doping, by means of by changing the temperature, uh, uh, by shining the light over this. So based on these things, doping, light, and all these, you can make different devices out of these semiconductor materials. If you can tune the conductivity, and you can make different type of devices out of this, like solar cell, photodetectors, transistors, and all these things you can make. Okay, and which of the following statement describes the essence of Moore's law? Moore's law, this is Moore said that the number of transistors in a semiconductor material, or this is the area, let us say 1 centimeter square area. Uh, in this area, so per unit area there the microchip, okay, the number of transistors will get doubled. Okay, so initially there were the size of the transistor, let us say, is is 100 micrometer. Okay, in the next in 1.5 year later it will be 50 micrometer size. Okay, so this is the, like, you can this number of transistors will per unit area will get doubled in every 1.5 years. This is the Moore's law. Okay, so the density of the, it is saying nothing but the density of the transistors. So from big computers, now you have handy mobile phones. Okay, from big hard disk, you have a small chips in your hands. That this is because of the this Moore's law, and this has happened because of the fabrication techniques that we are using these days. Okay, the fabrication techniques, the nanofab labs and all has because of them we have uh, uh, increased the density of the transistors. Okay, so now, so the relation between energy and wave vector in a reciprocal space for free electron is, okay, so this relation is E is equal to h cut square t square by 2m. Okay, so this is the energy. E is the energy, and this H cut is equal to h by 2 pi, which is the Hamiltonian the constant. No, this is I forgot this name for this one. This is the constant. H is the constant, and k is the reciprocal wave vector. Okay, this is the wave vector for in the reciprocal space, and this is the relation which is E is equal to h cut square by h cut square k square by 2m in between energy and the reciprocal wave space wave vector. Wait. Okay. So the relation between energy and this wave vector is parabolic. So parabola is y is equal to mx square or y is equal to kx square. This is a kind of relation, a parabolic equation. So E is equal to this is a constant and k square. So this is parabola. Okay, this is a parabolic relationship, these two. And now the another thing is the wave vector in the free space is this, and the movement of electron in periodic potential. Uh, Periodic potential is dependent on, okay, any whatever, if there is a periodic potential or anything, if it is periodic or non-periodic potential, the movement of electron is always dependent on the effective mass, not a real mass. So from this you can calculate the effective mass is equal to h cut square k square by 2 m star. Okay, from this relation, and this is dependent on, so this is the effective mass, and you can calculate from this d2e by this effective mass m star will come out to be h cut square by uh, d2e by dk square. Okay, this is the effective mass, and this is the direct this is the relation between the effective mass and this is the curvature d2e by dk square. This is known as the curvature. Okay, this is the term curvature which is used in mathematics, and from this you can just by looking at the curvature of the this conduction band or valency band, you can uh, you can uh, you can distinguish, okay, you can which has the more effective mass and which material has less effective mass of the electrons or holes. Okay, that is electrons will from for electrons you need to look at the conduction band. Okay, the curvature of the conduction band, and for holes you need to look at the curvature of the valency band. Okay, so there are some questions that we will see in this one. Okay. And the curvature of a conduction band in the EK diagram of material A. Okay, let us see that this is showing for the conduction band. Okay, this is a curvature. This is another curvature. Okay, curvature of conduction band uh, in a EK diagram of material A is more. Okay, the curvature d2e by dk square. This is the curvature. Okay, the curvature is more for this one. This is the more curvature. Okay, this is given this is material A and this is material B. Okay, d2e by dk square of material A is more. Okay, A is more. The effective mass, let us look at first at the effective mass, and what we have seen is m star is directly proportional to inversely proportional to the curvature d2e by dk square. Okay, so this m star is inversely proportional to the curvature. The curvature is more, the effective mass is less. Okay, the effective mass and mobility of material B. Material B has less curvature. Okay, it is given. if material B has less curvature, so the effective mass of M star B is greater than M star A. Okay, the effective mass is more of B. Okay, so is higher. Okay, effective mass is higher. Now let us come to the mobility. If the mobility is related to the with the, this M star, that is given by let me check once, but it is given by um, with the inverse relation tau something is there, tau by M star is there. There is one more term is there. So but one thing is the other things are constant, but which is not dependent on that. But the thing is the mobility mu is inversely proportional to the M star. Okay, mu is just imagine a heavy ball or a light ball, how or it can go through a something whatever it is. Okay, so just heavy more is the weight, so it will be very difficult for that material or that electron or hole to move. Okay, so heavier is the more is the effective mass, lesser will be the mobility. Okay, more will be the effective mass, lesser will be. Yes,
Sir,
yes. Okay.
hello.
हाँ सोमनाथ, yes सोमनाथ.
Sir, I think the term will be E into tau by M star. M star.
Yeah, I think yes. There will be E. Or let me check once. I can just tell you within a minute. That is no Q. That is Q. Okay. Okay. You are saying electron.
Electron charge. Electron charge, sir. Same.
E. Okay. Just a minute. Yes. That is E into tau into but divided by M star. Yes. Okay. E is the charge. Tau is the time. Okay. Or average time between the collisions. And M star is the effective mass. Okay. This is the formula for mu. Okay. What I wanted to tell you is which is the inverse relation. That's it. Okay. So
Mu and M star will be inverse relation.
yes.
Mu and effective mass is inverse relation.
Yes. Mu and effective mass has the inverse relation. That's what I wanted to tell. That's it. Okay. Okay. Now the effective mass of an electron in a periodic crystal. Okay. A periodic crystal can be okay. There are, let us see, the isotropic or anisotropic. If you see in isotropic terms, suggest that the effective mass is same in all the directions. Okay, in any direction, effective mass is same. And anisotropic terms is the effect. This effective mass when an electron is moving in this direction, there is certain effective mass. Let us say m star 1. Okay, and if electron is moving in this direction, this is, let us say, m star 2. This effective mass can be different in different directions because it will feel a different type of force. Let us say if let us say it is in hexagonal close packing, or the atoms are in this direction, there is a spacing between the atoms is a. Okay, but in this direction the spacing between the atoms is b, which is b is greater than a. Okay, B is greater than A. So the periodic potential is different in this direction. The periodic potential that this electron will see, that is different in this direction and in this direction. So the effective mass will be different in different directions. Also, that's why this effective mass can be anisotropic. Okay. So, and also captures all the quantum mechanical effects. Quantum mechanical effects is the thing that when you put an electron or in some surrounding, so it will feel some force, some kind of force because of the surrounding. Okay, so because of surrounding, when it moves, it will distort the surroundings, the effect of the surroundings. There will be an effect of the surroundings, and let us say there was an electron. It is moving in a free space, so there was no effect of the surroundings because it was in vacuum. Okay, there is no atom, nothing is there. So electron is moving very free. The electron is moving in a free space. But as soon as it is moving in certain media or certain material, if electron is moving, it is feeling some force. Okay, force due to the atoms from the surrounding electrons, holes, ionized atoms. So because of that, the mass of this electron is changed. Okay, so that effective mass, that m star, is capturing all these effects due to the surroundings. Okay, that is the thing, quantum mechanical effects. It captures all the quantum mechanical effects. Okay, so now this m star can be can be uh, can be used as m. Okay, can be used as for all the classical equations. Okay, this m star can be used in all the classical mechanical equations to solve the equations. Okay, to solve the anything. So it is capturing all these things. Okay, so and varies with that. No, it doesn't vary with time. Okay, it doesn't vary with time. So and it's same as the rest mass of an electron. No, it is not the same as rest mass of the electron because which is same in the free space only. Okay, because of yes.
Sir, I understand that it is not same as the rest mass because M and M star effective mass are different, sir.
Yes, yes. M star, we are talking
But sir,
about M star only.
but sir, it can vary with the time, na? Sir,
Mm-hmm.
if the electron if the electron effective electron pass through a different doping region, different sir means their material property, then it
Okay.
vary with the time.
No, vary with the time in the sense if it is at a location, if it cannot vary with the time for that material at that location.
Okay, okay. This is not material dependent.
Uh, In the same material it is.
Okay.
Yes, in the same material it is. We are not changing the material or anything. It is in the same material. Or if we are talking about we are talking about in, it is saying the periodic crystal. What you are talking about, what was your question actually?
Actually, my question is that when an electron moves through a periodic crystal,
Uh-huh.
it has
Mhm.
a number of effects are there
Mhm.
due to their mobility, due to their your condition of the ambient, due to their pressure. So
Ah.
inside the material,
Mhm.
it can.
No, but we are not considering all those effects, right? We are not considering the effective mass of an electron inside a periodic lattice. In a periodic lattice, if an electron is moving in this direction, let us say, okay, let me remove this one. Okay, let us say this is the periodic lattice. Okay.
ఎవరి బట్టలేసింది?
Someone mic is on.
ఎవరి వేసింది?
Deepti.
తీయంజు.
Hello, Deepti.
తీయమన్నప్పుడు తీయ అంతే, ఇక వద్దు ఆర్గ్యూ. ఏనైనా వేసుకో, నాకు సంబంధం లేదు, ఇడైతే వేయొద్దు. నేనైనా
Okay. Yes. Who was in the call? Acha, Somnath, you were asking something, right? Yeah. So,
Yes, sir.
so
Yes, sir.
in Somnath, we are looking for a periodic crystal, so it won't depend on time. Okay, it won't depend on time because there is it will find the same set of periodic potentials. Okay.
Okay, sir.
So in the same direction, it won't change with the time. The effective mass will be constant. M star will be constant.
Okay, sir. Okay.
But if there are, it is saying about if it would be saying for some other defective material, it would change. Definitely, it would change.
Okay, sir. Okay.
Yeah. Okay. So let us go on the next question. So what should be the temperature in Kelvin for all the energy states below the Fermi energy level to be filled? So if you remember, there was a, this is the, let us say, this is the energy. Okay, this is energy E, or in any direction, this is energy E or Fe. Okay, Fe. Fe is 1 for, okay, this Fe is 1. This is EF. Okay. So, do you remember Fe and E relation? Fe is the probability of finding an electron at energy E at temperature, at any temperature T. Okay, I'll write that. Fe is equal to 1 over 1 plus e raised to power E minus EF by KT. If you remember this thing. Okay, so at this is for T is equal to 0. Okay, this graph is for T is equal to 0. Okay, so below Fermi energy EF, below Fermi energy, the probability of finding an electron is 1. Okay, the probability of finding an electron is 1. So this is saying what should be the temperature in Kelvin for all energy states below the Fermi energy should be filled. So probability of finding an electron is 1. So all the states below Fermi energy are full. Okay, this is the, let us say this is the EF. Okay, whatever states below EF, these all are full. Okay, so this is what it is saying. So at 0 Kelvin only it is all the energy states are filled. So for temperature T is greater than 0, T is greater than 0. So what it will show is it will show some deviation. Okay, so it will hello.
Yes, sir. Repeat one time, sir.
Okay, what I am saying is the Fermi energy and temperature relation. Fermi energy, the Fe, this Fermi Dirac equation. Do you remember this one? Fermi Dirac.
Yes, sir. Yes, sir. Yes, sir. Yes.
This is the Fermi Dirac distribution. Okay, Fe is equal to 1 over 1 plus 1 e raised to power E minus Ef by kT. Okay, Ef is the Fermi energy. This is the Fermi energy, and at T is equal to 0, all the, this is the graph, if you can see. Okay, what I will draw it again. So for t is equal to 0, this is the graph, green, if you can see. Okay, if you
Yes,
plot
sir.
this
Yes.
Fe versus temperature at t is equal to 0, Fe versus E at t is equal to 0. Okay, if you increase the temperature, what will happen is, so it will deviate. Okay, so for t is equal to T1 greater than T2. Okay, so this was T2, and if so, something like this. Okay, so if you increase the temperature, the probability of finding the electron above T, above Fermi level will also increase. Okay, this is the thing. But at T is equal to 0, all the states will be filled. All the energy states below EF will be filled. This is the thing. So this is the EF, this energy state, and all the states below EF will be filled at T is equal to 0. Okay.
Okay, sir. Okay.
Yeah. So now another question. So what is the probability of finding an electron at an energy E equals to the Fermi energy EF at T is equal to, okay. So Fe, this is the probability of finding an electron at E is equal to EF, it is asking. Okay. So 1 over 1 plus E raised to power E minus okay.
Half, sir. Half.
E minus EF by KT. Okay, just put EF here. So EF minus EF will be 0. E raised to power 0 is 0 and 1 by 2. It will be 1 by 2 irrespective of any temperature. Okay, whatever be the temperature, but the probability of finding an electron at E is equal to F will always be half. Okay, so this is the correct answer. And so I will draw the graph as well. So this is EF. Okay, and this is 1 and this is Fe, F of E. Okay, this is E in this direction, and let me draw it with another color. So at T is equal to 0, this will be the graph. At T is greater than 0, so this will be the graph. Okay, but it will pass through 1 by 2. Okay, at EF is equal to 0, it will be 1 by 2. This is 1 by 2. Okay, so whatever be the temperature, it will pass through 1 by 2. Okay. Yeah.
Yes, sir. Yes, sir.
So now, so why the concentration of electrons at mid of the band gap for an intrinsic semiconductor is 0? Though the probability of finding an electron over there is half. So whatever we have seen in the previous one, what is it is saying? This is the semiconductor. This is the conduction band. This is the valency band. Okay, and this is the Fermi level EF. Okay, so the concentration of finding okay, why the concentration of electron at the mid of the band gap of for an intrinsic semiconductor means there is no no doping or no impurity is there in the intrinsic semiconductor. Okay, and 0. So the probability of finding an electron is 1 by 2. Okay, that we have seen in the previous one as well, but there is no electron in between these two. So that is because there are no states. Okay, there are no states available. The whatever states are available are above the conduction band and below the conduction band, below the valency band. So this is the band gap. Okay, where there are no states in the material. Okay, the conduction band, in between the conduction band and the valency band, there are no states available. Though the probability of finding it is 1 by 2. Okay, so this is no energy states are allowed at the middle. This is the one answer. And the electrons does not have sufficient energy. This is not the case. Okay, but electrons have the sufficient energy as they jump from here to here. Why they can't jump here? Okay, because they have sufficient energy. This is not the case because there are no energy states. The density of states is 0 at the yes, density of states is 0. Okay, there are no states available. The electrons does not have sufficient momentum. That is not the case. Give me. Okay, now the question number 12. Okay, assume the Fermi energy of level is 0.2 below the conduction band. Determine the probability of state being occupied at the okay. So this is the conduction band. This is the valency band, and the Fermi energy is this is the Fermi energy EF, and the distance between these two is 0.2 electron volts. Okay, so determine the probability. Oh, okay, it is asking the probability f of E. It is asking. Okay, f of E. So 1 over 1 plus E raised to power being occupied at conduction band at this position. It is asking. This is the E. Okay, so EC minus EF by KPT. Okay, so this is just solve this, put this 0.2. Okay, so that will be 1 over 1 plus E raised to power 0.2 divided by 0.026. Okay, so just solve this one, you will get the answer. Okay, just solve this one, you will get the answer. Okay, so do you have any more doubts in assignment 1?
Sir, one more time explain the 11th question, sir.
11th question, just give me a minute. Okay. Okay, density of states, this one. Okay, so in 11th question, what we are looking at is the concentration of electrons in the so what this it is asking. Okay, this is the conduction band. Okay, this is the valency band, and this in the mid gap there is the this is the intrinsic semiconductor. Okay, there is no impurity, then this Fermi level will be in the middle. Okay, this is EF. This is EF. So in conduction band, what do you mean by the band gap? Okay, the band gap is in between the conduction band and the valency band. There is the density of states in the conduction band. There are some density of states which can be occupied by electron, or they may be empty. Okay, so in each state there can be electrons. And in each state in the valency band there can be electron. Okay, so but in this band gap there are no such states. Okay, where the electrons can be there. Okay, so if there are no states, no electron can be there. Okay, just imagine you have a ladder. Okay, you have a ladder. So there are steps in the ladder. If there are the ladder has steps above this and below this, and in between there are no steps, so you cannot step on in between these two, right? Okay, so the same thing, electrons cannot be there because there is no state. Okay, there are no empty boxes, we can say. There are no empty boxes where we can put the ball. Got the point?
Yes, sir. Yes, sir.
Okay. Can we move to the next second assignment?
Sir, one time show the answer of 12, sir. Answer of 12.
12th one is this 4.5 into 10 raised to power minus 4. That is the answer.
Yes, sir. Yes, sir. Okay, okay.
Okay, so if you solve this one, you will get that one. Okay.
Yes, sir. I can solve.
Okay. So now let's move to the next one. So I need to reshare the screen. Mm. Can you see the screen or is it blank?
It is blank, sir.
Okay. Still blank?
Now it is visible.
Okay, now it is visible. Okay. So now let's move on the next one. Uh, Next assignment. So this is the assignment 2. So the intrinsic carrier concentration. Okay. Intrinsic carrier concentration. This is the any semiconductor. This is the valency band. This is the conduction band, and this is the Fermi level EF. Okay. So this is silicon. Silicon has 1.1 electron volts of the this band gap. Okay, but if you this is the a direct question that you need to remember yourself, that the intrinsic carrier concentration whenever there is no doping. So what is the Ni? There is Ni or Pi. Okay, this is Ni is equal to Pi is equal to 1.5 into 10 raised to power 10 per centimeter cube. So this is the carrier concentration, or if you are seeing this is the centimeter square, the carrier concentration is always in the centimeter cube. Okay, so this is minus 10. So there is no such concentration that is like 1.5 into 10 raised to power minus 10. Okay, so and this is another this is the concentration when we dope the semiconductor with Na acceptor or Nd. Okay, so that can be 1.5 into 10 raised to power minus 10 raised to power 15 per centimeter cube. Okay, and so that you need to remember. Okay, or you need to solve different equations. First, you need there are some NC and V effective density of states in the conduction band, in effective density of states in the valency band, that are already calculated. If you want to go through that, there is a book, Donald and Neiman. If Donald and Neiman, okay, these are the writers. So if you want to go through, you can go through the book as well. So there are so many different problems you will find in that. So that is a very good book. So you can go through that book as well. So the net charge in an N-type semiconductor is, okay, the N-type semiconductor, whatever is the dopant is. So let us say ND. ND is the will create this is the donor, and D means donor. So ND turns into ND plus an electron. Okay, so it will donate an electron. That's why it will give you an N-type semiconductor. Okay, so initially what to say, phosphorus, right? Phosphorus will give you some phosphorus has 5 this is pentavalent uh, atoms will give the N-type doping. Phosphorus will change into P plus plus an electron. Okay, so this electron will be in the conduction band, and this is the immobilized ion. Okay, this is the ionized impurity or the immobilized ion, or it will stay there at its position. So let us say this is a semiconductor, and here there was an atom, the dopant impurity. Okay, so electron will go out of its bound because this pentavalent atom, the one electron is free, so that electron will go and it will move inside this. Okay, but this ionized impurity will stay there, but electrons can move. Okay, so but electron is still in the semiconductor, and this is still in the semiconductor. This ionized impurity is still in the semiconductor. So whatever it is, so both are there. This Nd plus as well and electron as well. So it will be a neutral. Okay. Ionized ion is also there and electron is also there in the semiconductor itself. Okay. So net charge is 0. Always 0. Okay. Do you have any doubt in this one? Okay, let's move.
No, sir. No, sir. Actually, sir, you want to say that in case of N-type semiconductor, there will be some immobile ion plus electron donor as a donor atom.
Yes, yes.
But
But both are there in the semiconductor.
yes, a donor atom is there, acceleration both are there.
Yes. So that's why it is neutral.
Okay, sir.
Okay. So the probability of finding an electron below the Fermi level at the Fermi level. Okay, what we have seen in this one, this was the 0 Kelvin. So this is the Fermi level. This is energy E. This is EF, and this is 1. Okay, this is the F of E. The graph. This is the probability. Okay, the probability of finding an electron below Fermi level. This is the below Fermi level. This is the below Fermi level is 1. Okay, and at the Fermi level is 1 by 2. And this is the Fermi level. At the Fermi level is 1 by 2, and above Fermi level is 0. Okay, so 1, 1 by 2, and 0. This is the answer. Okay, so the first one is the answer. Okay, and the next one is the curvature of the conduction band. Curvature of the, okay, this is the conduction band and is more than the curvature of the valency band. This is the curvature of the valency band. Okay, this, yes, this is more, this is less. The curvature of the conduction band is more than the curvature of the, in the EK diagram material. The effective density of states in the valency band is, okay, this is the valency band, the effective. First, let's see the effective masses of this one. Effective mass of hole and effective mass of electrons. Okay, this will M star E, M star H. Effective mass of hole will be given by the curvature of the valency band. Effective mass of electron will be given by the curvature of the this conduction band. Okay, so the curvature is more in the conduction band. No, more. The curvature of the conduction band is more. So effective mass of electron is less. Okay, than the effective mass of the hole. M star H. Okay, and one more thing, the effective density of states, it is asking. Effective density of states, if I will tell you, is the Nc in the conduction band, Nv in the valency band. This is the effective density of states in the conduction band, and this is the effective density of the states in the valency band. And this is directly proportional to M star raised to power 3, right? If I am not wrong, this is the relation. Okay, and also you can go through the book as well. You will find this relation. Okay, Nc, there will be some Nc and Nv. Okay, so the effective density of states, more the mass, effective mass, more will be the density of states. Okay, so the curvature is less. For the curvature is less, the holes for the curvature is less, the effective density. So okay, the effective density of states in the valency band is always greater than, because the effective mass is of holes is more. Okay, so this is the correct answer. You got the point, or
if the curvature is less, it indicates that the mass of that particle is more. So the effective density of state will be
More.
data for that particle.
Okay, if the effective mass is less, the density of states will be less. If effective mass is more, the density of states will be more, because it is
Okay,
direct
yes, sir.
relation of 3 by 2, raised to power 3 by
Okay,
2.
okay.
Okay,
This is NC into NV.
not NC into NV. Okay, I'll show you the. Okay, give me a minute. I will show. Give me a minute. Can you see this one? There is a presentation. Hello.
Sir, yes, sir. I've given that.
Yes, sir.
Okay, just my laptop is not charging. Give me a minute. Okay, now you can see. Okay, this is the effective density of states in the conduction band. Okay, can you see whatever I am writing? This thing.
Yes, sir.
Okay, so this is the NC. This is NV, effective density of states in valency band. Okay.
Okay, sir. Okay.
And this is direct relation Mn star raised to power 3 by 2. This is Mp star or Mh star, whatever you can denote for the holes, by 3 by 2. So this is for valency band, this is for conduction band. So that the relation is raised to power, effective mass raised to power 3 by 2. That's what I want to convey.
Okay, sir. Okay.
Okay. Now, okay, let's move to the next one. Okay, an acceptor atom Na. Okay, this is the acceptor atom accepts an electron and changes to Na minus. Okay, so an acceptor atom accepts an electron and becomes negatively charged. Okay, this is the answer. Got it? Whatever
Yes.
the
Yes, sir.
Okay. So a donor atom Nd, whatever a pentavalent atom is, Nd changes into Nd plus electron. It donates an electron. Okay, it donates electron and turns to positively charged ion. Okay.
Okay, sir.
Yes. A material has a band gap of 0.7 electron volts. Okay, this is a conduction band. This is the valency band, and this gap is 0.7 electron volts. Okay. So now two different samples A and B. Okay, let us let us say this is A and this is B. Okay, this is conduction band, this is valency band, this is conduction band, this is valency band. Okay, so two different samples A and B of this material has been doped with impurities dopants. Okay, sample A has EC minus EF. EC, this is the EC. EC minus EF. This EF is 0.2 electron volts. This is 0.2 electron volts. Okay, and sample B has this is, let us say, 0.5 electron volts. Okay, the conduction band and the EF. Got the point?
Yes, sir.
Okay, and if the Fermi, it would be an intrinsic, the Fermi level would be in the middle, and that would be in 3.5 electron volts below the conduction band. Okay. Yeah, got the point or not?
Yes, sir.
So now it is the Fermi level is near to conduction band. That means this is an N-type semiconductor. Okay. And
Okay,
in
sir.
this case, the Fermi level is more near to the valency band, which is 0.2 electron volts above the valency band. Okay. So this is a P-type semiconductor. Okay. Wait. So this is a P-type semiconductor. So based on the above information, both the samples A and B are P-type? No. Okay. Sample A is P-type? No. Sample A is N-type. Sample A is N-type. So this is sample A is N-type and sample B is P-type. This is the correct answer. Got the point?
Okay, sir. Okay, sir.
Okay. So let's move on the next one. So a semiconductor material has been doped with an acceptor impurity. Acceptor impurity is accepting the electron and making the material P-type. Okay. Acceptor impurity, okay, Na plus electron turns into Na minus. Okay. So this is the ionized impurity which is accepting an electron. Okay. This is negatively charged ion. Okay, so it is accepting the electron and making the material P-type. Okay, so P-type material it is making. Okay, the dopant concentration at point A is this much and then gradually reduces to 10 raised to power 16. Initially at point A, this is the point. Okay, let us see. This is point A and this is point B. Okay, so material is P-type. Material is P-type. Let us okay, and similar this. Okay, which of the following correctly depicts the Venn diagram at material under equilibrium? Just note this term, under equilibrium. Under equilibrium, there is no current flows. Okay, under equilibrium, there is current is not flowing. So this Fermi level will be constant. Okay, this Fermi level EF is constant. Okay, and one more thing is given at point A, the concentration is more, and at point B, the concentration is less. Okay, at point A. So although it is P-type, so the Fermi level will be more near to the conduction, more near to the valency band. Okay, will always be, and here at this point A, it will be more near to the valency band. At this point, it will be a bit far from the valency band. So this will be the valency band will look like this. So at this point, it will be the distance between, or not the distance, the gap between the Fermi level and the valency band will be less, and at this point the gap between the Fermi level and the valency band will be more. Okay, and this valency band, this conduction band will equally follows like this one. Okay, so this will be the correct answer. So let us see. So in this one, this is an N-type semiconductor. This is an P-type semiconductor, but it is a bit this one at point B, the concentration is more than the point A. Okay, this is again an N-type semiconductor. This is an P-type semiconductor with concentration of the dopant concentration at A is more and then the dopant concentration at B. Okay. Got the answer? Got the point? Or
Okay.
should I-
Yes, sir. Yes, sir.
Okay. Now, under high doping, so this is the approximation that I think sir has taught in the lecture. So that is the Joyce-Dixon approximation when there is EC minus EF is less than 3 kT. So you cannot apply there is a Boltzmann approximation that is used to solve the equations. Whatever we have taken this concentration of electrons N naught or P naught from the equations. Okay, so N naught and P naught, which is equal to NC into e raised to power EF EC minus EF by kT. Okay, so and P naught is equal to NV into e raised to power EF minus EV by kT or something like that. Okay, minus, I think this there will be a minus sign or that you can check. So these are this approximation. We directly wrote F of E in this manner. So that is because of the Boltzmann approximation, and that holds only if EC minus EF is greater than 3 kBT. Okay. So this should be greater than 3 kBT. This is the gap between the conduction band or valency band, conduction band and the Fermi level, or valency band or the Fermi level should be greater than the 3 kT. So then only this approximation holds, this Boltzmann approximation. And below that, if the gap is lesser than that, then another approximation comes, that is the Joyce-Dixon approximation. Okay. That is the Fermi half integral is solved. Now let's move to the another one. So three semiconductor materials A, B, and C have their band gaps. Okay, one. This is two. Okay, this is A. This is B, and 1.1 electron volts, which is a bit. Okay, this is 0.7 electron volts. This is 3.5 electron volts, and this is 1.1 electron volts. Okay, so this is C. And for the same device design, any of the device, let us say this is a diode, we are making diode. Okay, diode or transistor, anything. Okay, so which of them will give a lowest and highest leakage current? Lowest and highest leakage current. So if there are charge carriers are more what to say, at room temperature. At room temperature, if the electrons Ni, the intrinsic carrier concentration is more, in that case there will be a more leakage. I don't remember the equation, but there is a thermal sort of equation. I forgot the name. But if this is the thing that if the intrinsic carrier concentration is more, then there will be a more leakage current. If the intrinsic carrier concentration is less, then there will be a less leakage current. So in 0.7 electron volts, so the carrier concentration Ni is proportional to e raised to power Ez band gap. Okay, more is the okay, less no, inversely. Okay, that I need to check once. Just give me a minute. I have the equation. Not the third one, second one. Okay, Ni is equal to, okay, I'll write that down. Okay, so Okay, Ni or Pi, anything. Ni is equal to square root of Nc into Nv into e raised to power minus Eg by kVt. Okay, so this is the equation. So less will be the band gap, less is the band gap, more will be the Ni concentration. Okay, Eg lesser, more will be the band this concentration Ni. Ni is the intrinsic carrier concentration, and more is the band gap, that is the 3.5. More is the band gap, less will be the Ni. Okay, so that you can directly, if you just think of the electron from the conduction band, from the valency band, needs more energy to jump over. Okay, in this case, for and thermal energy is 0.026 electron volts. So the probability of jumping in this case, it is a very difficult process. Okay, so in this case, it will be easily jumped, and the concentration, carrier concentration in the conduction band, the electron concentration in the conduction band for 0.7 electron volt will be more than the 3.5 electron volt. Okay, so more is the carrier concentration, more will be the leakage current. Okay, A has the more leakage current and B has the least leakage current. Okay, highest is A, lowest is B, and highest is A. So this is the answer, C. Okay, this is the answer. Got the point?
Okay, sir.
Okay, so okay, so this, how many questions are left? Two more. This one. Okay, so now the next one is, which of the following are the consequences of the degenerate doping in a semiconductor? Degenerate doping. So okay, so degenerate doping means when the Fermi level itself is too close or is in the conduction band on the valency band. So when we dope a semiconductor, let us say when we dope the semiconductor, so in doping, let us say it is an N-type doping. N-type. Okay. In N-type doping, so when you dope the semiconductor, there is an donor level is created at this just below the conduction band. Okay, this is the donor level, not the valence Fermi level. This is the donor level which is created near to the conduction band. And if the density is less, so then there will be a single donor layer, single layer level. So if the density, the doping concentration is more very high, okay, so then it will split. This will split into a band. Okay, this will split into a band, and there will be a band narrowing. So it will mix up with the conduction band. So this band will mix up with the conduction band, and so the effective band gap will be this much only. Okay, because there is there are energy levels till this point, and the effective band gap is this one. So there is a band, not the band expansion. This is the band narrowing, because band gap has reduced because of the very high doping. Okay, because of very high doping, the band gap is narrowing. So potential perturbation in energy band diagram. This is the potential perturbation only. Okay, because of the impurity atoms that we have added, which has created its own band, and this own band of the energy. Okay, own energy band. So that is the potential perturbation. Okay, so and the material starts to behave more like a metal than a semiconductor. Yes, because as you have doped this one very high, so there are electrons. Okay, there are electrons in these states, and above that there are empty states. Okay, so the situation is like there is a band which was empty. This is the conduction band which was empty. Now you have created another band because of the doping, which is full, so which is overlapping with the conduction band. Okay, and this band is full and this band is empty, so there are energy levels which can jump, so it will more like a conduction. This is a valency band and this is a conduction band. Okay, it is more like that. There is a full band and this is empty band, so it will more behave like a metal. Okay, got the point?
Sir, third point one more time, sir, please.
Okay, this metal one.
No, potential perturbation. Perturbation in the energy.
Okay. Potential perturbation in the energy band diagram is okay. So the potential perturbation, I think this is a more physics term. So whatever I know in electronics term, so that I will tell you. So potential perturbation is because of when you dope a semiconductor, you create a imbalance in the potential. So there was initially there was a what to say, a there was a there was previously there was okay. So there are potential okay, periodic potentials. Okay, there were periodic potentials. Okay, so when it was intrinsic, okay, intrinsic semiconductor, there were potential because of that there were atoms. Okay, there were atoms. Because of that, there are periodic potential. But when you dope the semiconductor, you have removed this atom, okay, and of silicon, and you have added another atom that has potentially perturbed the sequence. Okay, this potential perturbation, and when you do more and more of this one, initially it was very less. When you dope more, and it is creating more and more perturbations in the periodic potential. Okay, in the periodic potential, it is distorting the periodic potential. Let us say it is distorting the periodic potential, and the energy band diagram, if you dope the more, so these atoms, whatever you have doped, these starts interacting with each other when they are very close, in the close proximity. If you dope more, they will be close, and they will make their own band. Okay, and that own band, this band, so it will overlap with the conduction band. Okay, so that is the band narrowing, and it is distorting this band diagram. That's it.
Okay, sir.
Okay. So, and you got the fourth point. This material
Yes, sir,
starts
yes.
behaving like. Okay. Okay. Let us see this last question in this one. I think this is the last question. Okay. So, a silicon.
Sir, repeat again. Sir, repeat again 11 question number
Okay.
for
11
metal.
metal one. Okay.
Yes,
So,
sir.
okay. Okay.
Yes.
I'll tell you the metal part again. Okay. So, this is the conduction band. This is the valency band. Okay. Valency band. This is the conduction band. And when you dope the semiconductor, you are creating an extra level of the donor level. Okay. This is the donor level. Okay. If you are, this is an N type, you are creating the donor level. Okay. So this donor level is a single level. If the atom, the density of or the concentration of the dopant is less. Okay, because they are not interacting at each with each. But this is a band. Okay, there are many energy levels. This is a band. There are many energy levels because of the silicon atoms. But this is a band because of the, let us say, phosphorus. You have the phosphorus are very less, but silicon, this is silicon, this is silicon, this is silicon, this is silicon. Okay, and these phosphorus atoms are not interacting that much with each other. Okay, But if you don't dope it more and more, so these will start interacting with each other again. So, and that will split this energy as well, this energy level as well. So this split in energy levels will create a band. Okay. So this band will overlap with the conduction band. So this is the degeneration. Okay. This will overlap with the conduction band. So this there were empty states in the conduction band, and these are the full states. These states are full. Okay. So these bands are overlapping. This is the conduction band, and the band which was created by the donor atoms. Okay, so this band was full and this was empty. So now it is more behaving like an matter. Got
Yes,
the point?
sir. Thank you, sir.
Yeah. Okay. Now a silicon sample is doped with both Na. Na plus electron is Na minus. Okay, and Nd plus electron. Okay, so it is doped with the P type as well as with N type. Okay, so the doping concentration of 10 raised to power 18. This is the 10 raised to power 18. This is 10 raised to power 16. Okay, so have you heard about the compensation, carrier compensation or dopant compensation? Okay, so in dopant compensation,
No, sir.
what happens is just let us say you have doped a material or whatever it is with 10 acceptor atoms, Na, 10 acceptor atoms, and 8 Nd donor atoms. Okay, so Na plus electron will give you Na minus. Okay, so Nd will give you Nd plus electron. Okay, so 8 of these will compensate. So this is acceptor, this is donor. So 8 electrons will be taken by this. Got the point? So
Yes, sir. Yes, sir.
8 electrons will compensate 8 acceptor atoms. Donor atoms will, so there will be effectively only 2 donor atoms, 2 acceptor atoms will be left. Got the point?
Yes, sir. Yes, sir. Yes, sir.
So this is the same thing. Na minus Nd. You need to do Na minus Nd here. So that will be so at what temperature it is asking. So let us we are assuming the complete ionization is happening there. Majority carrier concentration is okay. So there will be 100 into 10 raised to power 16 minus 10 raised to power 16. So there will be 99 into 10, 9.9 it should be 0.9. Okay, 0.9 into 10 raised to power 18 will be the this acceptor now, the P type. This will be the answer. This should be the answer. And okay, this will come Ni square. Okay, and now N is equal to N naught. N is equal to P naught P divided by Ni square. Okay, so from here you can calculate. So this will be the answer. So because this is the P type and 10 raised to power 18 will be the 0.9. Actually, it should be 0.99. It is given 0.9. Okay, this is the answer. This is the correct answer. Okay. So any doubts till now?
Sir, how we calculate 2.5 into 10 to the power?
Okay, this one. Okay, so this one
Yes.
n is equal to P naught
N by Ni square, sir.
P naught by Ni square. Okay, from here you can calculate. So P is 0.9 into 10 raised to power 18 divided by 1.5 into 1.5, 2.5 or divided in, okay,
10 to 20, sir. 10 to 20.
10 raised to power 20. So now you can calculate P naught. No, it is ulta. Ni square by P naught.
That's sir.
Ni square by P naught. It is ulta 2.25 divided by into 10 raised to power 20 divided by 0.9 into 10 raised to
2.5 into 10 to 2, sir.
okay, it will come 2.5 10 raised to power 2. It will come.
Yes, sir. Thank you, sir.
Okay.
Thank you, sir.
Okay. So till now, do you have any other doubts? So if you have any,
No, sir.
okay.
The lecture will be the recorded lecture recorded will be available later, sir.
So now only I will upload in 2 hours or 3 hours. I will upload this one. Okay. Or maybe tomorrow. By tomorrow,
Okay.
I'll upload this one.
Sir,
Thank you, sir.
Yes, Sanjeev.
sir, actually,
Thank you, sir.
Yeah. Yes, Somnath.
yes, sir. Actually, sir, you can, after this upload, sir, you can take another class for, means, sir, in this week, because there will be some holidays there. So the 3, 4, 5, 6, the remaining assignment we'll discuss, sir. It will be beneficial for us, sir.
Remaining assignment I'll discuss on Tuesday. Tuesday 6 to 8 p.m.
Okay, sir. Okay, sir. Okay, sir. Thank you, sir.
6 to 8 p.m. remaining assignments I will discuss. Okay.
Okay, sir. Okay.
Any other doubts?
No, sir. I have to study, sir. After that, actually, all of you have to study, sir. After that, if you have any question, I can ask you Tuesday, sir.
Yeah, sure. Okay. Yeah. Thank you for
Thank
attending.
you, sir.
Yeah. Thank you for attending. Okay, you can leave.